Alrighty guys, welcome to the very first section of calculus. Now before we get into all the cool stuff like derivatives, integrals, finding areas, finding slope lines, all that sort of stuff, let's focus on one of the most important concepts of calculus, one that we need for all the other stuff, and it's called limits. Limits. So what is a limit? The actual idea is actually not too complicated. Let's take a graph. Let's say y equals x squared. So let me draw my xy plane right here. There's that. And so this is going to be y. This is going to be x. Now let's take y equals x squared. So that will look something like this, where you have a parabola extending like that, and extending like that. And let's take a certain x value. Let's say we find an x value of 2. And then according to our graph, that means that y value has to be equal to 4. Obviously, this is not drawn to scale. So we have our point that looks like that. And let's say we approach this value, this x value, using the graph all the way from the left side. So you're going to get closer and closer to 4 as you keep going along this side. And then let's say we approach it from the right side. And basically approach it, we get closer and closer to it and see what the y value actually is. And so in this case, we get a y value of 4. And so basically you would say the limit as x approaches 2 will be equal to 4. And the way you write it will be something like this. So you're going to say the limit, L-I-M stands for limit, as x goes to 2, that's how you write as x and then this arrow for 2, of f of x, and let's define f of x to be x squared, is going to be equal to 4. That's basically how you do it. It's a pretty easy concept. All you do is you just basically approach the value from both sides, and then you get a certain value. Now you might be thinking, that's not too bad at all. Like, what's so hard about that? Well, trust me, it gets a lot harder. I mean, not super hard, but let me show you a little bit harder an example. That'll kind of give you just a taste for how things are really when you solve limits. Let me just delete all this right here. Alright, let's do another example. And this one I'm going to do something called a piecewise defined function. And basically, you might know this from pre-calculus, it's basically a function that has different values based on where you are along the graph. And it has this really weird looking function. Usually it's not all together, usually it's all these separate things right here. And I'm actually going to use an example from the book. Now this piecewise defined function is not, the actual function itself is not defined. It could be, we just don't have it. But I am going to draw the graph for you. So it's going to look something like this. So this is going to be our y, and then this is going to be our x. Alright, y and x. And I'm just going to draw a bunch of different values right here. So I'm going to do 1, 2, 3, 4, 5. And then I'm going to go all the way to 10 on this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4, 5, 6, 7, 8, 9. Alright, so we have those. And now let's actually draw the function itself. So what I'm going to have this super weird curve. And let me kind of show you what I mean. So it goes from 0, this is 0 right here, and it's going to go all the way to 3, 3. So right here, so it's going to look something like this. And then right here, we're actually going to have a hole. So what the hole basically says is that the function goes to this value, but at that certain point is actually not defined. It's actually defined somewhere else. And so where we have it is defined is going to be right here. So basically this is saying the function is defined at this value at that point, but the reason why there's a hole here is that the progression leads to here. And we'll get to that later. And then we're going to have a curve down all the way to 5, 1. So it's going to go all the way down to here. And then here we actually have a dot, so the function is defined right here. Alright. Pretty weird, huh? And then we're going to have, at that same point, there's going to be another progression. and at the point it's going to be 5, 4, there's going to be a hole because we're going to start on another sort of trajectory, and it's going to go all the way down to 7, 2. So it's going to look like this. And then here we're going to have another hole because the function, so this time it's kind of weird, the function is actually not defined at all at this value. And then we're going to go all the way up to 7, 4, and there's going to be another hole because remember the function's not defined there. And then we're going to have another sort of curve all the way down to 10, 1. So it's going to look like this. Just like that. And that is the value of 1. I know it doesn't match up super well. And then we're going to have this sort of asymptote right here, where it kind of, if I were to just draw a dotted line all the way up here, it starts at the infinite value, like this, and then goes all the way, but doesn't quite hit the x-axis. It's going to go like that. Alright, so that's our function. It's pretty crazy, eh? So basically, just like we did with the last one, let's find a few limits. So, for example, let's find the limit. Let's think about this. As x approaches 3 of f of x. So this is not quite as simple as our y equals x squared example, because you see here that it approaches this value right here from this side, and then approaches the same value from that side as well, but the function is actually not defined at that point. So what is the result? So here's one of the most important concepts of a limit. You never look at the value that is defined at that certain point. You always look at the value that you approach for both sides. So from this side, you see that it approaches the value of 3, and then that side you see it approaches the value of 3 as well. And so we actually disregard that point entirely. Even if there's a hole here, even though we know it's not what's called a continuous function, which we'll definitely go over in depth later, that doesn't matter because you see that it approaches the same value from both sides, and then you know that it's totally fine. So in our case, this is actually going to be equal to 3. Alright, that's one. Let's go on to the next one. And now let's find the limit as x approaches 5. So let me just delete this thing. Alright. And what is the limit as x approaches 5 of f of x? So here, you see that it goes all the way down and approaches this value of 1, right? But then, if you look at the right side, it approaches this value of 4. So what's the thing here? Because there's going to be two different values. Well, the thing with the limits is that if you approach with one value on the left side, and then you approach with another value on the right side, that limit actually does not exist. So in this case, we're actually going to say, because there's two different values that it approaches, this value does not exist. I'm going to write D and E for short. It's pretty standard. Does that make sense? Because you're approaching two different values from two sides, and there's an inconsistency there, and there's no way that you can actually have a limit that exists. So that's that. Let me delete that. Alright, let's go to another one. What is the limit? And maybe we can just kind of see this just by eye, because it's a very similar case. As limit approaches 7. Because here, you see that it goes all the way to this value of 2, right? But then on this side, you can see that it goes to a value of 4. So we would also say the limit does not exist, right? And now let's look at as the limit approaches 10. See that it goes all the way over here to value, it looks like 2, but it's actually 1. It approaches 1, but then see here that it approaches an infinite value. So even still, it's still going to be two different values, so the limit does not exist. So this first one right here, where there was this weird thing happening, that was the only case where the limit actually did exist, because even though it was a discontinuity, and we'll cover the details of what discontinuity is, but even though there's something weird happened, we could still find the limit because it approached the same value from both sides. But in all these other cases, it didn't. Now, I want to introduce another thing that's kind of interesting with a limit, because you can split a limit up into two different limits. So see here how we've been doing limits as it approaches the left side and the right side? We can actually do it where it just approaches the left side or just approaches the right side. The way you write it is going to be like this. You're going to find the limit. Let's say like for 10, for example. X approaches 10. And if you want to observe from the left side, you're going to just write this minus right here. And so minus is going to be for left, plus is going to be for right. And so if we were to do this of f of x, what is our answer? Our answer is going to be 1 actually, because it's going to get closer and closer to that value as you go from the left side. But what about the limit as x approaches 10 from the right side? So you're just going to write the plus there. It's going to get up and up and up here. Actually does exist. It's not a non-existent limit. It's going to be a value of infinity. That's a horribly drawn infinity symbol, but that's the different values that you get for those. And remember how we concluded that it's undefined as a whole because these are not the same value? But you can still split it up and you see that there's actually 2 different values that actually do exist. That's basically solving a limit from the left-hand side and from the right-hand side. Alright, so that's basically solving limits, and obviously there's cases where you're going to get much harder and harder examples, but that's pretty much it when it comes to actually solving for a limit. And one more thing I just want to introduce before we go here, and before we go into all the problems, is that when it comes to a limit, there's a couple different ways of solving for them. And in the next few sections, we'll go over all those different methods. But one method that you'll be using for your homework is the idea of numerical tables. And so basically, what we've been doing so far with limits, we've basically just been looking at the graph and observing from the graphs to see what the limit actually does and what the limit is. But there's another way that you can actually do it. You can actually use your calculator, and for this I'd recommend the TI-83 or 84. Those are pretty standard for calculus classes. And then using those calculators, you can go to your table setting and then set up a table and look at all the values that are super, super close. Like for example, if we were to approach 5, for example, I would say look at the y values when it says like 4.9, then 4.99, 4.999. You can get even closer and closer and see what the actual value is. And then you can go from the right side and say you can do 5.01, 5.001, 5.0001, and get closer and closer to that value, and then see what the values are. And if they approach a same value, you can say the limit actually does exist and it's this certain value. Or if they're different values, you probably say it doesn't exist. Or let's say it goes down really, really far, it gets smaller and smaller and smaller to the negative values, you probably say it goes to like negative infinity. Or if it does that with the positive values, you could probably say that it goes to positive infinity. So you can decipher a lot just by looking at the tables. And trust me, once we get to the examples, I'll show you exactly how to do it. One thing that I'll do in the problems is I'll actually use a site called Desmos. I actually have it open right here. And so this is one that you can actually see different things. You can set up tables, you can set up graphs. It's pretty fun. And we'll do that in all the other problems. Don't worry about it. But that's pretty much it for limits. It's basically just looking at a graph or maybe looking at a table and seeing what a value approaches. People make it to be a lot harder than that, but it's not really too bad. And obviously in the examples, we're going to get to trickier examples and stuff that requires a little more thought, but we'll get into all that. So it's not a problem.